Algebra 2, Chapter 1, Section 3, Equivalent Expressions. In this video, we will talk about equivalent expressions. Two expressions are equivalent if and only if they have the same value for every value of the variables. Now this should say variables, sorry. Please don't judge my spelling. So this is something that's so important you should memorize this. And I will try to make a point of every definition you should memorize, but most of the time in the book, a critical definition will be in a blue box. This is one case where it's not, so you might want a box or star in your book that this is a very important definition. Also, the book does not include this statement, and only if. However, this is very important logically for the definition to be correct. Two expressions are equivalent if and only if they have the same value for every value of the variables. So let's contrast equivalent with equal. We've already talked about when expressions are equal. Two expressions were equal when they had the same value for some particular value of the variables. Remember we talked about how 2x equals 3 when x equals 3/2, right? So, equivalence is very different. 2x is not equivalent to 3. To be equivalent, these two sides, these two expressions, must be the same for all values of the variables. All, or every. So 2x is not equivalent to 3. Unfortunately, algebra uses the equal sign to mean equal and equivalent. For instance, your book will write someplace, perhaps, x times x equals x squared. This is actually a statement of equivalence. X times x is equivalent to x squared. In other words, they have the same value for all values of the variables. Another way of thinking of equivalence is the two things that are equivalent can be substituted freely for each other, and they will never change the truth of an idea or of an equation, or even the value of an expression. Because of this confusion between the equal sign, meaning equals, and the equal sign meaning equivalence, I will always try to use either the equivalence operator, this three-barred equal sign, or the biconditional operator, which is the if and only if symbol, to mean equivalence, to help us distinguish equivalence from equals. The book will not do this for you, but I will try, because they are different things. And the book does mention this, but it doesn't give you a different symbol. And that is because of long history of using the equal sign to mean many different things in mathematics. You might think mathematics has no subjectivity. However, there are symbols that are overloaded that you need to know the context in order to understand what the symbol means. We'll encounter this again in function notation. So let's do an example real quick of equivalence. I already did x times x is equivalent to x squared. We could also say a over 2 is equivalent to 1/2 times a. And we might ask why. In fact, we may have a homework problem or an example, as in example 1, that asks us why. Why is a over 2 equivalent to 1/2 times a? We could see that if we wrote an equation, a over 2 equals 1/2 over a, that if we were to multiply the equation by 2, we would get this statement, a equals a, because 1 times a is a. This is the statement that we should want to see to show equivalence. because a and a are freely interchangeable. They have the same value for all values of the variables. If a is a variable, of course a's value is the same as itself by the law of identity, right? Something is itself. A is always equal to a, which means a is equivalent to a, or freely interchangeable, which shows that a over 2 is equivalent to 1/2 times a. So showing that two expressions are equivalent is rather more complex than simply equals, because we must now use rules of algebra or arithmetic or logic to prove or show that each expression is the same for every possible value of the variables. Now, I'm not going to be strict with you being very formal with these proofs or with this showing. Really, here to show means to prove. But I want to see you attempt to give me the rule, maybe describe it like by the rule of multiplication, or by the way by the way division works in the homework, to show me, and also any quizzes we have, why two expressions might be equivalent. To show that two expressions are not equivalent is much simpler. All we have to do is find one counterexample. We just need to find a value for the variable or variables where the two expressions have different values. And there may only be one such thing, but that may be the thing that makes two things not equivalent. For instance, let me go show you. What if I ask you, is this expression, x divided by x, equivalent to this expression, 1? Well, at first glance, you might think, oh, sure, because 2 divided by 2 equals 1. 3 divided by 3 equals 1. 7 divided by 7 equals 1. But just by showing examples that make them equal does not prove equivalence. Okay, so by the definition of equivalent expressions, we can't just find values that make them equal. We have to either, by the definition of division, explain, or some other algebraic or arithmetic thing we understand, explain why x divided by x has to always be 1, or we should need to show a counterexample. This one's a little tricky. The counterexample here is 0. 0 divided by 0 is not equal to 1. In fact, it's not equal to anything. When we divide by 0 in algebra, this has no definition. In other words, dividing by 0 is meaningless in algebra. It has no meaning. A way of thinking about this in regards to language would be if I said, put on your Algebra. Well, that doesn't mean anything to you. It's meaningless. Okay, so dividing by 0 is a meaningless operation. It doesn't have a meaning in algebra, so it can't mean 1. It doesn't mean anything. This doesn't mean anything. So because division by 0 doesn't mean anything, x divided by x is not equivalent to 1. And we can write x over x is not equivalent to 1 because when x equals 0, 0 over 0 is not equal to 1. And then we can circle this as our answer. Now, if your entire work is your answer, maybe circling it's a little bit silly. But if you have all this other stuff here, this helps me see what it is you're answering. Let's do some more examples that have to do with equivalent expressions. First, let's look at example 3 in the book. It says, show that 2 over x plus y is not equivalent to, and I'm going to use this equivalence, and I'm going to slash it out, not equivalent to 1 over x plus 1 over y. Remember, not equivalent's easy. To show not equivalent, all we need to do is come up with two numbers, one for x and one for y, that show that the two sides are not the same. They have different values. Now, we can't choose 0 and 0 because then we get division by 0. If we choose 1 and 1, we'll have maybe a good start. So let's try that. X equals 1 and y equals 1. So we'll try these. We get 2 over 1 plus 1 on the left-hand side equals 2 over 2. 2 divided by 2 is 1. On the right-hand side, we have 1 over 1. Remember, x is 1. And 1 over 1 because y is 1. 1 divided by 1 is 1, so we have 1 plus 1, which equals 2. So to show that they're not equivalent, all we need to show is that when x is 1 and y is 1, then the two sides are not equal. There's your counterexample, and here's why. This is the work I want to see, but it's not really part of the answer. But I do need to see it to know that you actually proved it. Now, what about example 4? It says the expressions 2x squared minus 5x plus 3 and x squared, that doesn't look right, x squared minus 2x plus 1 have the same value when x is 1 and when x is 2. So you might wonder, what am I writing this about? This is the symbolic logic form of and. Okay, so I'll often on the blackboard or in the slides just use this symbol to mean and. Because this symbol that we use in English a lot looks like plus or like that. And this is a fast way of writing it. How can you remember this as and? It looks like an A with the crossbar removed. Okay, so that symbol means and just another aside, this is the symbol for logical symbol for or. Looks like a V. Okay, so 2x squared minus 5x plus 3 and x squared minus 2x plus 1 have the same values when x is 1 and when x is 2. Okay, so there's two examples of them being the same. Does that make them equivalent? So the question is, are they equivalent? Okay, so we can go through and plug in the numbers and show that they have the same values at 1 and at 2. But what's more interesting is trying a different number and seeing if we get the same thing. Because if we don't get the same numbers for each side, they're not equivalent. And that's the answer, and we're done. So let's start with the left-hand side. Working with the left-hand side, let's start by putting in just the number 0. Why 0? 0 is so easy to evaluate. So trying 0, we get 2 times 0 squared minus 5 times 0 plus 3. And on the right, we have 0 squared minus 2 times 0 plus 1. Well, 0 squared is 0, times 2 is 0, minus 5 times 0 is 0. So all these things just go to 0. Same over here, all that stuff is 0. We have 3 on the left and 1 on the right, and these things are not equal, and so the answer is not equivalent. Two expressions are not equal when x equals 0. And I actually picked a different counterexample than the book did for example 4. They used 3. I did 0 because it's faster. So what good is this idea of equivalent expressions? The main good is that we can now substitute different things for each other when we do show they're equivalent. And we can do a word problem here which may demonstrate this. So let's look at example number 5 in the book. We have to convert from miles to kilometers, Abby doubles the number of miles, this is example 5m, and decreases the result by 20%. So we're going to go from miles to kilometers. We have Abby's way of doing it. Abby doubles miles, so doubles the miles, and then decreases the result by 20%. Okay? So she takes 20% off. So she takes the number she had before and takes off 20%. So she multiplies this number by 20% and subtracts that out. Okay, so Renato has a different mechanism or method, of converting from miles to kilometers. First, he takes the number of miles and divides by 5, and then multiplies the result of that by 8. Okay, so part A says write an algebraic expression. I just kind of did it as I was doing the word problem, so I'll just circle that as my answer to this part. Let's try not to circle off of it. So that was part A. Part B, decide if the two methods give the same answer. Well, they can only give the same answer for all values of meters, if they are equivalent. They have the same value for all values of the variables. So let's take Abby's way, 2m minus 2m times 0.2, and see if we can do operations on it which will keep the truth value or the equivalence the same to get to Renato. If we can do that, we can show how they're the same by sort of a string of equivalences. So we can make an equivalent expression to 2m minus 2m times 0.2 using the rules of arithmetic and algebra we know. For instance, we can rearrange multiplication. 2 times 0.2 times m. We can even write what we're doing over here. Rearrange multiplication to say this is an operation that is equivalent on expressions that will never change the truth value. 2 times 0.2 is the same as 2 times 2 over 10. 0.2 is 2/10, or it's 20/100, which is 4 over 10, or 0.4. Now we have 2m minus 0.4m, and if we remember, we can add coefficients of variables from algebra and not change the truth value. So we can add 2 and negative 0.4, or we can subtract, if you like to think of it that way, to get 1.6m. Now maybe we might want to think backwards. Renato has m times over 5 times 8, so we need to get to a fraction. So if we make this a fraction, 1.6 is 16/10 by definition of decimals. And then by fraction simplification, we can divide the top and bottom, the numerator and the denominator, by 2 and get 8 over 5m. Numerator and denominator by 2, by the same number. And 8 over 5m is the same as m over 5 times 8 by reordering multiplication and division, which is allowed when we talked about that, when we talked about PEMDAS, or the order of operations. So here we have a nice little sketch of a show or a proof of why these are equivalent. We might write therefore equivalent. Circle that. That means therefore, or there's QED, there's lots of ways to end proofs.